Welcome to Sleepy Science Facts. It's wonderful to have you here, where we can explore the quiet wonders of our universe together. Feel free to make yourself comfortable, letting go of the day's worries. If you find this calming, a gentle reminder to like and subscribe can help us continue on this soft journey through science. Some materials, known as ferromagnets, have a special ability to hold on to their magnetism. This property comes from tiny regions inside these materials called magnetic domains. At the atomic level, these domains are groups of atoms that have their own magnetic moments, which means they can act like tiny magnets. When these domains are aligned in the same direction, their magnetic effects combine, creating a stronger overall magnetism in the material. Even without any external influence, these domains can stay aligned for many years, quietly maintaining their state. The arrangement within the material contributes to a consistent magnetic property that remains stable over time. Changes in temperature or surrounding conditions do not easily disrupt this balance. As a result, the magnetism found in such materials can persist, showing a remarkable resilience that invites deeper exploration into the nature of magnetism itself. Certain species of fish have a remarkable ability to sense the Earth's magnetic field. This unique skill aids them on their long migrations, guiding them back to their spawning grounds with remarkable accuracy. Inside these fish, there are special cells that contain tiny mineral crystals. These crystals interact with the magnetic field, creating signals that the fish can perceive. This perception allows them to navigate vast oceans, often traveling thousands of miles. As they journey toward their birthplace, the fish can remain attuned to the subtle shifts in the magnetic field. This natural compass is so finely tuned that it helps them find their way even in murky waters or when faced with strong currents. The internal mechanisms that allow for this sensing are delicate and finely crafted, ensuring these creatures stay on course. The ability to read the Earth's magnetic field underscores an intricate connection between these fish and the world around them, revealing the quiet wonders of natural navigation. As they continue their journey, the balance in their bodies remains harmonized, ready to follow the ancient pathways that guide them homeward. When two magnets come close together, an invisible force begins to act between them. This force can either pull them toward each other or push them away, depending on how they are aligned. The phenomenon occurs without any physical contact, which speaks to the unique nature of magnetic interactions. Each magnet is surrounded by a magnetic field, an area where its influence can be felt. These fields extend into the space around the magnets, allowing them to exert force even when they are some distance apart. The arrangement of the magnetic poles plays a crucial role. Like poles repel each other, while opposite poles attract, creating a delicate balance of attraction and repulsion. This interaction is a beautiful example of how forces can operate at a distance, reminding us that there are energies at play that we cannot see. The quiet dance of magnets, influenced by their hidden fields, provides a glimpse into the subtle forces shaping the physical world. The gentle interplay of these magnetic fields continues, ensuring that the delicate balance remains, quietly echoing the mysteries of nature that surround us. Magnetic fields are shaped by the charges within materials, and these charges respond uniquely to certain properties of the substance. Different materials exhibit varying magnetic characteristics, influenced by their atomic structure and electron configuration. For most materials, these magnetic properties remain stable under normal conditions. The energy within the magnetic field is consistent, providing a steady presence that aligns with the inherent nature of the material. However, when exposed to extreme electromagnetic forces, the stable behavior of these charges can shift. The delicate balance of attraction and repulsion may be altered, leading to new magnetic behaviors. This ability to adapt, while generally stable, allows materials to respond to different energy levels and environments. As these charges interact, they create fields that gently fluctuate in strength or direction, but usually return to their natural states once external forces are removed. This quiet resilience reflects a harmony within the structure of matter, providing a subtle reminder of the complexities that exist, even when they go unnoticed. The magnetic world, ever present yet largely unseen, continues to surround everything, waiting to unfold as we drift into deeper understanding. Within a magnet, the internal structure consists of countless tiny magnetic domains. These domains can be viewed as individual regions that possess their own magnetic orientation. When a magnet is not magnetized, these domains are arranged rather randomly. Each domain is like a small compass needle, pointing in different directions and canceling each other out, resulting in no overall magnetic effect. When a magnet is created, an external force influences these domains, causing them to align in a uniform direction. This alignment brings harmony to the once chaotic arrangement, allowing the magnet's strength to emerge. As the domains settle into their organized state, the magnetic field they produce becomes stronger and more stable over time. This stability is a reflection of the delicate balance between the interactions of the domains. Even as they work together in this synchronized manner, their internal interactions persist quietly, maintaining the magnet's properties. The tranquility found in their uniformity is a reminder of the steady forces at play, resting gently within the fabric of the magnet, ready to reveal their nature as we explore further. Certain animals possess a remarkable ability known as magnetoreception. This intrinsic skill allows them to perceive the Earth's magnetic field, guiding their journeys across vast distances. Within nature, this ability has been observed in a diverse range of creatures, including birds, sea turtles, and even some insects. These animals seem to sense the invisible lines of force that encircle the planet, using them as tranquil pathways on which to navigate. For birds, this instinct plays a vital role during migrations. As they travel thousands of miles, the magnetic field serves as a constant reference, helping them maintain direction and reach their destination safely. Sea turtles, with their age-old journeys, also rely on this instinctive navigation to return to their nesting sites after years at sea. Insects, like certain species of bees, also display a sensitivity to magnetic fields. This ability enhances their understanding of the environment, helping them find food sources and communicate effectively within their colonies. As these creatures move through their world, they embody a quiet connection to the Earth's magnetic essence, skillfully attuned to forces that remain unseen yet profoundly impactful. Each subtle movement reflects a bond with the planet, instilling a sense of harmony as they journey onward in their natural rhythms. Ocean currents, a fundamental part of the Earth's dynamic systems, partake in a subtle dance with the magnetic field. These currents, flowing through vast bodies of water, can take on varying temperatures and salinities, contributing to shifts in the Earth's magnetic signatures over time. As the currents move and change, they interact with the magnetic field, leading to alterations in its distribution. These slow changes in the magnetic profiles of the ocean can have a gentle influence on local marine life. For some organisms, these magnetic variations might be a guiding force, gently helping them find their way across the vast ocean expanses. For others, the changes could shape the environments they inhabit, affecting how they thrive in their habitats. As the currents ebb and flow, they create a backdrop of constant transformation, blending the physical properties of water with the unseen forces of magnetism. In this quiet interplay, life within the ocean continues its rhythm, reflecting the delicate balance between the currents and the invisible threads of magnetic energy surrounding them. This peaceful coexistence is a testament to the intricate connections present throughout our planet. Permanent magnets, solid structures of organized atoms, hold their magnetism through a delicate balance of order. Over time, however, the continuous movement of atoms, influenced by thermal agitation, can lead to a gradual decline in their magnetic strength. This thermal energy, present even in seemingly still environments, causes the atoms within the magnet to vibrate gently, displacing the alignment that creates magnetic fields. As the years pass, these small fluctuations can disrupt the stable arrangement of atoms that defines a strong magnetic force. Each slight movement contributes to an overall diminishment in the magnet's effectiveness, a slow and unhurried transition. This process offers a glimpse into the intricacies of internal magnetic energy, showing how even the most steadfast qualities in nature can change with time. Observing this gradual fading serves as a reminder of the subtle shifts that occur in the world around us, where the interplay of energy and movement is continuous, even when imperceptible. The lasting existence of a magnet, while slowly evolving, reflects the gentle rhythms of change that flow through all matter, inviting quiet contemplation on the nature of stability and transformation. The density of magnetic materials is a steady characteristic, generally holding firm at a consistent value, measured in kilograms per cubic meter. This property serves as a defining aspect of the material, shaping its fundamental nature. While this density tends to remain constant, there exists an interesting interplay with external factors, especially temperature. As temperatures rise or fall, the molecules within the material respond, their vibrations changing with the heat. These vibrations can lead to slight variations in density, a subtle dance of particles adjusting to new energy levels. The structure of the material, while fundamentally unchanged, experiences minor shifts that ripple through its composition. Even a small change in temperature can prompt the atoms to draw closer or move slightly apart, influencing how densely they pack together. Such variations in density may be modest, yet they reflect the inherent relationship between the material and its environment. This slow, gentle adaptability highlights the dynamic nature of physical systems, even in states that seem stable. The quiet resilience within magnetic materials invites contemplation, reminding us of the hidden movements at play, always ready to reveal the softly shifting world around us. Volcanic activity holds a subtle power in shaping local magnetic fields. As molten rock or lava flows from the depths of the earth, it carries with it iron-bearing minerals that respond to the Earth's magnetic pull. When this lava reaches the cooler surface, it begins to lose heat, and as it cools, it solidifies into rock. This transformation is not merely a physical change, it also locks in the magnetic signature of the Earth at that moment. Over hundreds of years, as layers of lava accumulate and cool, these magnetic signatures become permanent, weaving a tale of geological history into the very fabric of the Earth's crust. The minerals, now firmly set, maintain their magnetic orientation, preserving a snapshot of the Earth's magnetic field during the time of their formation. This delicate balance of temperature and geological processes results in a rich tapestry of magnetic memory beneath our feet. Such interactions between volcanic activity and magnetic fields enhance our understanding of the planet's dynamic nature, showing how earth and sky influence one another. The calm, enduring presence of these geological formations invites a sense of wonder about the ongoing processes beneath the surface, always quietly shaping the world in which we exist. Magnetic fields, measured in units called Teslas, possess a remarkable quality of stability in settings where their environment remains undisturbed. When temperature fluctuations and electrical noise are kept at bay, the strength of these magnetic fields can remain consistent over extended periods. This consistent presence is rooted in the stability of the magnetic forces themselves. In ideal conditions, a magnetic field can provide a clear and reliable representation of its surroundings. The delicate balance of particles and energies creates a serene environment, allowing for the gentle flow of magnetic lines of force. It is this unchanging nature that provides insights into the physical reality of the universe. The quiet energy radiates through space, remaining largely unaffected by transient disturbances. Such stability is an intriguing aspect of the invisible world surrounding us, suggesting that even the faintest of forces has its own rhythm and consistency. This calm reliability invites contemplation, adding layers to our understanding of the natural world, much like a gentle breeze that whispers truths without interruption. Each magnetic field holds a story, waiting patiently in the serene backdrop of existence. The sun, a vast and luminous sphere, experiences long-term fluctuations in its magnetic field that unfold over decades and centuries. These variations create a subtle yet profound influence on solar activity, characterized by cycles of solar flares and sunspots, each a reflection of the changing magnetic dynamics at play. As the magnetic field shifts, it affects the solar wind, the continuous stream of charged particles flowing outward into space. This gentle breeze from the sun interacts with the Earth's magnetosphere, shaping its characteristics over time. The magnetosphere, in turn, acts as a protective envelope, safeguarding our planet from solar radiation and other cosmic elements. The dance between the sun's magnetic changes and the Earth's magnetosphere is a slow, intricate rhythm. These long-term transformations create a backdrop for the natural phenomena observed on Earth, from auroras shimmering in the polar skies to variations in satellite operations. Each cycle of this magnetic behavior weaves into the greater tapestry of our cosmic environment, offering a serene reminder of the interconnectedness of celestial bodies. The gentle undulations of solar activity occur far above us, yet they ripple through the fabric of our world, reflecting the quiet dynamics of nature. Natural phenomena such as solar storms arise from the sun's energetic activity, releasing bursts of charged particles that travel through space. When these solar storms reach Earth, they interact with the planet's magnetic field, creating a temporary disturbance. This momentary upheaval can produce beautiful displays of light in the night sky, but the long-term effects may be more subtle. Repeated exposure to these solar storms can gradually weaken certain areas of the magnetic field. Over many years, this ongoing interplay creates variations in the magnetic strength around our planet. Regions where the field is diminished may find themselves more susceptible to cosmic radiation. While these changes are usually gentle and unfolding, they weave into the fabric of the Earth's magnetosphere, crafting a complex relationship between our planet and the dynamic activity of the sun. Each solar storm contributes to this slow transformation, a reminder of the vast influences surrounding us. In this quiet interaction, one can sense a continuous flow of energy and change, an intricate dance that keeps the essence of our planet ever evolving. The solar activity we observe is guided by a rhythmic pattern known as the Hale cycle, which spans about 22 years. This cycle is a reflection of the sun's magnetic field dynamics, entrusting it with a graceful ebb and flow. Within this longer cycle, there are two distinct 11-year sunspot cycles. These cycles mark the peaks of solar activity, periods when sunspots are more numerous, and the sun's magnetic field is particularly vibrant. At each peak, a fascinating shift occurs. The magnetic fields of the sun undergo a reversal, a process where the magnetic north and south poles switch places. This reversal is part of the intricate dance of the solar magnetic field, intertwining the sun's energy with its magnetic properties. During this time, the complexity of magnetic interactions intensifies, affecting various forms of solar emissions. As the cycle progresses, the dance of solar magnetism continues, creating a harmonious, if subtle, influence on the solar system. Each phase of the Hale cycle reflects not just solar activity, but the enduring nature of magnetic forces, reminding us of the interconnectedness of celestial rhythms. The gentle transitions within this cycle allow us to appreciate the quiet power and beauty that reside in the stars above. The Earth's geomagnetic field has experienced a remarkable degree of stability over vast stretches of geological time. This magnetic field, generated by movements within the molten outer core, envelops the planet, extending far beyond its surface. It acts as a protective barrier, reducing the impact of solar winds and cosmic radiation. Its steady presence creates a familiar orientation point for many species navigating their environment. This stability plays a crucial role in the lives of various organisms, guiding them along migration routes across great distances. Birds, for example, may use the geomagnetic field as a tool for navigation during seasonal migrations, relying on subtle changes in the magnetic field to find their way. Other animals, such as turtles and certain fish, also tune into the magnetic signals, sensing the Earth's magnetic patterns as they travel through vast oceans or across land. As the geomagnetic field continues to maintain its enduring nature, it symbolizes a constant presence in a world that often shifts and changes. The quiet assurance of this magnetic stability stretches across time, inviting us to consider the underlying forces that shape our planet and the rhythm of life it sustains. Superparamagnetic nanoparticles, tiny particles that can exhibit magnetic properties when exposed to strong magnetic fields, possess unique characteristics that distinguish them from larger magnetic materials. Their small size, often in the nanometer range, allows them to easily interact with their surroundings, responding swiftly to magnetic fields without retaining significant magnetization once those fields are removed. This behavior allows them to be manipulated with precision in various situations. Within their distinct properties lies the potential for remarkable applications, particularly in biomedical contexts. When introduced into the body, these nanoparticles can navigate through biological systems with increased efficacy. In the presence of a magnetic field, they may cluster together or move towards specific locations, making them ideal candidates for targeted drug delivery. This targeted approach can help ensure that medication reaches the desired area while minimizing impact on surrounding tissues. The ongoing exploration of these nanoparticles highlights their intriguing behaviors under various conditions, revealing insights into their interactions with biological systems and magnetic forces. Their ability to operate effectively within complex environments opens the door to further understanding of their roles and potential, gently inviting curiosity into the ongoing dialogue of science. The core of a magnet is composed of atoms arranged in a specific orderly pattern known as a crystalline structure. This organization creates a dense framework where atoms are tightly packed together. The regularity of this arrangement is crucial as it contributes to the magnet's overall strength and stability. Within this crystal lattice, individual magnetic domains can align more harmoniously. Magnetic domains are small regions within the material where the magnetic orientations of atoms are consistent. In a well-structured core, these domains work together, enhancing the magnet's ability to hold its magnetic properties. When exposed to an external magnetic field, the domains can align themselves in harmony with this field, momentarily enhancing the magnet's strength. After the external influence is removed, the crystalline structure helps maintain this alignment, preventing the magnet from losing its magnetic qualities easily. Such a robust internal structure ensures that the magnet remains effective over time, with minimal fluctuations in its properties. The gentle interplay between the atoms within the core and the arrangement of the crystal lattice establishes a foundation that supports the magnet's enduring capability, inviting exploration of its fascinating characteristics in a tranquil, seamless manner. In certain uncommon scenarios, individuals may experience a phenomenon called magnetophosphenes. This occurs when strong magnetic fields interact with the visual system of the eye, leading to unexpected sensations. Under these conditions, the brain may interpret the stimulation as flashes or patterns of light, even in the absence of a direct external source. These visual impressions arise from the intricate workings of neural pathways. When exposed to a significant magnetic field, electrical signals in the brain can be altered. This alteration may lead to temporary visual disturbances that manifest as vibrant flashes or shimmering shapes. The experience is fleeting, often vanishing once the strong magnetic influence is removed. The underlying mechanisms that bring about magnetophosphenes involve the delicate balance of electrical activity within the visual cortex. These interactions highlight the complexity of human perception and the varied ways that different forms of energy can influence it. Each instance serves as a reminder of the fascinating interplay between our biology and the physical world, inviting peaceful contemplation of our connection to the unseen forces around us. Permanent magnets are remarkable for their ability to retain a magnetic field over extensive periods of time, independent of any external energy source. This permanence stems from the internal arrangement of their atoms, which have a special orientation. In these materials, the magnetic domains, or tiny regions within the structure, align in such a way that they contribute to a strong overall magnetic field. Once created, this organized state can be sustained without requiring additional energy. Due to this stable arrangement, permanent magnets can remain magnetized for years, even decades, while retaining their strength. The interaction of electrons within the atoms creates a balance that holds the magnetic properties intact. In time, some external factors, such as extreme heat or physical shock, can affect a magnet's ability to hold its field. Yet, under normal circumstances, the robust nature of permanent magnets allows them to offer consistent performance. This continuous presence of a magnetic field invites reflection on the remarkable properties of materials found in nature, where stability and consistency can exist over long durations, gently encouraging the mind to drift into serene thoughts. The Earth's crust is in constant motion, a gentle dance of tectonic plates shaping the planet over vast stretches of time. As these plates shift, magnetic minerals within them can change position. This movement is so gradual that it often eludes immediate observation. The deep-seated forces beneath the surface guide these changes, transforming the landscape ways that may remain invisible to the eye. As layers of rock and sediment are uplifted and folded, the arrangement of magnetic minerals is influenced. The minerals, sensitive to the Earth's magnetic field, can record the direction and intensity of that field as they form. Over millions of years, the shifting crust can obscure the original magnetic signatures embedded within these rocks. Each transformation adds to the story told by the ancient magnetic fields, offering insights into the planet's dynamic history. This continuous geological activity invites contemplation, framing a deeper understanding of how the Earth itself changes in its own timeless rhythm. Through this ever-evolving landscape, the mysteries of the past resonate softly, inviting exploration and reflection. Some materials, such as ferrites, possess unique properties that allow them to maintain a stable magnetic state, even when environmental conditions change. These ferrites, which are primarily composed of iron oxides, exhibit their magnetic characteristics in a consistent manner. As temperatures fluctuate or external magnetic fields shift, ferrites remain relatively unaffected, creating a dependable framework for their magnetic behavior. This reliability arises from their crystalline structure, which forms distinct patterns at the atomic level. These patterns help preserve the orientation of magnetic moments within the ferrite, ensuring that these moments align in a steady way. This internal organization provides a sense of stability, even in varied settings. The capacity of ferrites to retain their magnetic qualities in changing environments makes them intriguing subjects for study. They carry with them an essence of permanence that contrasts with the transience often observed in other materials. This enduring nature subtly reflects the balance that exists within the physical world, a balance that continues to evolve yet remains rooted in its core properties. The gentle unfolding of such characteristics invites a deeper appreciation of the quiet strength found in these materials. Electromagnets are fascinating structures that come to life through the flow of electric current. When electricity passes through the wire coils wrapped around a metal core, a magnetic field emerges. This magnetic field can hold a quiet strength, allowing the electromagnet to exhibit magnetic properties while the current flows steadily. However, the endurance of this magnetic state is connected to the continuous supply of electricity. As the electric current moves through the coils, it creates a moment of defined magnetism. This force is not permanent. It gently fades away once the current ceases. The relationship between the electricity and the magnetism creates a delicate balance, one that shifts and changes with the flow of energy. This temporary nature allows for a variety of behaviors, as the magnetic field can expand and contract with the varying levels of current. The core of the electromagnet exhibits unique characteristics, responding to the strength of the current and the arrangement of the wire coils. Each pass of electricity whispers through the structure, creating a dance of magnetic energy that is both transient and stable while it lasts. The interplay between electric flow and magnetism speaks to the intricate world of physical forces, revealing how energy interacts within its own quiet realm. Each moment holds the potential for transformation, leaving space for further exploration of these serene principles. Geomagnetic excursions represent subtle shifts in Earth's magnetic field, occurring at intervals of approximately 20,000 years. During these excursions, the magnetic field may deviate from its usual orientation, leading to temporary changes in the magnetic forces that envelop the planet. These variations are not permanent, but are rather short-lived, allowing the field to eventually return to its more stable state. Within this framework, the magnetic field plays a silent role in influencing various terrestrial phenomena. Animals animals attuned to the magnetic patterns of the Earth rely on these consistent signals to navigate their journeys across vast distances. These small yet significant changes during excursions can prompt adjustments in their behavior, affecting migration patterns and exploration. In addition to their impact on animal navigation, geomagnetic excursions subtly intertwine with the Earth's geological processes. They are part of the natural rhythms of our planet, quietly reflecting the dynamic nature of the magnetic field. As the Earth continues its patient spin through time, these gentle fluctuations serve as reminders of the shifting forces at play. Each excursion whispers of a world in constant motion, creating space for further inquiry into the harmonious mysteries that unfold beneath our feet. In the gentle dance of the Earth's crust, magnetism serves as a vital thread woven into the fabric of tectonic plate motions. Within rocks, magnetic minerals quietly align themselves with the Earth's magnetic field, capturing whispers of its fluctuations over time. This alignment creates a permanent record, much like a time capsule, encapsulating the magnetic state of the planet at that moment. As tectonic plates shift and grind against one another, the forces unleashed influence not only the formations of the land, but also the orientation of these magnetic minerals. The history recorded within the rocks reflects the intricate ballet of geological activity unfolding across epochs. Over extended periods, these magnetic alignments can help reveal patterns of movement, offering insights into the ongoing evolution of the planet. Through this delicate interplay of magnetism and geological forces, the Earth continues its timeless transformation. Each subtle shift carries with it the echoes of a planet in a state of gentle motion, inviting curiosity about the natural rhythms and processes that shape its surface, a quiet reminder of the wonders that lie beneath, waiting to be explored. Ferromagnetic materials, like iron, possess a unique internal structure that allows them to maintain a stable magnetic state over extended periods. At the heart of this phenomenon lie small regions called magnetic domains. Within each domain, the magnetic moments of the atoms align in harmony, pointing in the same direction. When a ferromagnetic material becomes magnetized, many of these domains adjust their orientation to create a collective alignment. This arrangement can persist for years, like quiet soldiers standing in rows, faithfully preserving the magnetism even in the absence of an external magnetic field. The stability of these domains is influenced by factors such as temperature and the presence of impurities, yet under typical conditions, they exhibit remarkable resilience. As time flows gently over these materials, the magnetization can remain intact, quietly holding onto its characteristics without any need for reinforcement. This enduring nature contributes to the intricate tapestry of the physical world, revealing the subtleties of how magnetic properties can remain ingrained within a substance, ready to be discovered in every turn of the Earth's journey. The calmness of this process invites a deeper reflection on the silent, enduring forces that weave through our surroundings, setting the stage for understanding the world in its serene complexity. Magnetic fields, shaped by the sun's activity, flow through space like unseen currents, interacting with the delicate web of communication systems above our planet. When solar events occur, such as solar flares or coronal mass ejections, these fluctuations create ripples in the magnetic environment. As these changes unfold, they can disturb the flow of signals traveling through satellite communications, causing a subtle yet noticeable effect. The signals, designed to traverse vast distances, often rely on stable magnetic conditions to maintain their strength and clarity. However, as these magnetic fields fluctuate, the the signals can experience gradual degradation. This can manifest as a reduction in quality, a soft fading of clarity, or even intermittent interruptions in communication. Over time, the gentle tug of these changing magnetic conditions may lead to an overall weakening, reminding us of the intricate dance between solar activity and the technologies we often take for granted. These quiet influences serve as a testament to the delicate balance of forces in our universe, where the cosmos interacts with the systems that relay information. As the fields ebb and flow, they create a serene reminder of the interconnectedness of our world, inviting us to consider the soft rhythms of nature that exist beyond our immediate perception, always ready for discovery. The Earth's magnetic field serves as a protective barrier, gently interacting with charged particles streaming from the sun. These particles, often released during solar storms, embark on a journey through space, drawn toward our planet. As they approach the magnetic field, they find themselves entangled in an intricate dance, guided toward the polar regions. Here, near the Earth's poles, the charged particles dive deep into the atmosphere, colliding with gas molecules. This interaction releases bursts of energy that create stunning displays of light, known as auroras. The colors vary, painting the night sky in soft greens, brilliant reds, and delicate purples. These shimmering lights are not merely momentary flashes, they are ongoing expressions of the dynamic relationship between the sun and the earth, leaving lasting impressions on our atmosphere. As this relationship continues, the auroras shift and swirl, embodying the calm yet powerful interplay of celestial forces. They are reminders of the beauty that can arise from such interactions, revealing how the fabric of our atmosphere is shaped by the gentle influence of solar activity. In this way, the Earth's magnetic field cradles these charged particles, creating a breathtaking spectacle that gracefully unfolds in the darkness. There is a serenity in this cosmic exchange, inviting thoughts to drift in the quiet embrace of the universe, always unfolding, always ready to tell us more. Stellar magnetic fields arise as stars rotate, their motion generating magnetic forces that extend far into space. These fields form as charged particles within the star's interior move and swirl, creating complex patterns that can persist for millions of years. Over time, the stability and strength of these magnetic fields can influence a star's behavior, affecting the flow of energy and the dynamics of its outer layers. The magnetic field acts like a hidden architect, guiding the star's development and evolution. It can create phenomena such as stellar flares, which are bursts of energy released when magnetic lines of force reconnect. This interaction shapes not only the star, but also its surrounding environment, influencing how material is expelled into space. Even in the vast emptiness of space, these enduring magnetic fields play a role in the silent choreography of celestial bodies. They can affect the interactions between stars and clusters, harmonizing their movements across the cosmos. Ultimately, this relationship unfolds quietly, with each star maintaining its magnetic identity through the ages, an ever-present force guiding its journey through the universe. All of this happens in a calm and gentle rhythm, creating a seamless flow of energies that is both ancient and profound, silently reminding us of the vastness of the cosmos. The cores of neutron stars exist under conditions of immense pressure, far surpassing anything we encounter on Earth. In these stellar remnants, the intense gravitational forces compress matter to extraordinary densities. Here, protons and electrons combine to form neutrons, creating a dense sea of particles that also nurtures powerful magnetic fields. The pressures in these cores can exceed 10 circumflex, 15 Teslas, a number so vast that it dwarfs the strongest magnetic fields produced by human technology. Within this tightly packed environment, the behavior of particles shifts. Neutrons, with their unique properties, interact in ways that amplify the magnetic presence, often leading to intricate structures within the neutron star. These magnetic fields develop stability, becoming a lasting feature that can influence the star's surface and even its rotation. This relationship creates a unique dynamic where the magnetic interactions shape the neutron star's character over time. As the star spins, the magnetic field stretches and forms intricate patterns, a silent ballet occurring deep within its core. The pulsations of these fields can resonate through space, sending ripples into the cosmos. Even as the neutron star evolves, the echoes of these extreme pressures and their formidable magnetic fields remain significant, quietly reflecting the depths of the universe's mysteries. Each of these elements exists in a tranquil state of being, waiting to be explored in the soft light of understanding. Static magnets, in their stillness, exert a quiet yet profound influence on the materials around them. Each magnet produces a magnetic field, an invisible presence that extends into the space nearby. This field can either attract or repel certain materials, depending on their magnetic properties. When an object comes within range, the force of the magnet can gently guide it closer or push it away, creating a subtle dance of motion. As these interactions occur over time, configurations of objects begin to change. When a magnet attracts a piece of iron, for instance, the iron is drawn toward the magnet's surface. This gradual movement leads to a new arrangement, altering the placement of surrounding objects as they respond to the shifting forces. The presence of a magnet can nudge items into line, promoting harmony and order within their vicinity. Complex phenomena unfold quietly as the materials settle into new positions, influenced by magnetic forces. Over extended periods, these adjustments can lead to stable patterns, inviting a sense of equilibrium to the space they occupy. In this serene manner, static magnets contribute to a gentle evolution in the arrangement of nearby materials, creating a landscape shaped by the subtle power of attraction and repulsion. The calm of these interactions lingers softly in the air, inviting curiosity about their delicate balance. The solar magnetic cycle unfolds over a period of approximately 11 years, enveloping the sun in a rhythm of magnetic change. During the early phase of this cycle, the sun's magnetic field begins to strengthen. This gradual intensification sets the stage for a variety of solar phenomena. Sunspots emerge on the solar surface, appearing as dark patches that signal areas of intense magnetic activity. These sunspots can vary in number and size, revealing the dynamic nature of the solar surface. As the cycle progresses, solar flares may occur, releasing bursts of energy into space. These flares represent brief moments of intense activity caused by the release of magnetic energy stored in the sun's atmosphere. With each cycle, the dance of sunspots and solar flares creates a tapestry of activity that epitomizes the sun's own internal clockwork. Throughout this period, the magnetic polarity of the sun also flips, creating a magnetic environment that influences the sun's behavior. This cycle, though spanning years, operates on a gentle rhythm, drawing the attention of solar observers and inviting contemplation of the celestial body's evolving nature. Observations during these years reveal the inherent harmony and complexity of the sun as it continues its timeless journey through the cosmos, endlessly shifting and transforming. In this quiet cycle, the calming energy of the sun resonates, leaving a space open for reflection and wonder. Neodymium magnets, a fascinating type of magnet, draw their strength from a combination of rare earth elements, specifically neodymium, iron, and boron. The arrangement of these elements plays a crucial role in creating their unique magnetic properties. Within the internal structure, the atoms align in a specific pattern that enhances their magnetic abilities. This organization contributes to a powerful magnetic field that remains remarkably stable over time. As a result, neodymium magnets exhibit strength far exceeding that of traditional magnets. Their ability to generate a strong magnetic pull allows them to hold objects with ease, demonstrating a quiet efficiency in their function. They possess a hardy nature, capable of maintaining their magnetism through various conditions, making them reliable components in different environments. The internal dynamics of these magnets echo through the arrangements of bonds between atoms, producing a symphony of magnetic force. As they interact with one another, their energy remains focused and directed, illustrating the intricate balance found within. This harmony between structure and function continues to invite curiosity and admiration, allowing for a deeper appreciation of the simplicity and complexity interwoven within these small but powerful objects. The gentle dance of their magnetic fields lingers softly, holding a serene space for contemplation. The concept of energy density in magnetism serves as a gentle reminder of the quiet strength found in different types of magnets. Neodymium magnets, with their remarkable arrangement of elements, hold energy in a way that is much more concentrated than traditional ferrite magnets. This means that within a small volume, neodymium magnets can store a greater amount of magnetic energy, allowing them to exert powerful forces despite their size. As time passes, however, the magnetic properties of these materials may begin to change. The energy density can gradually decline, affecting the magnet's strength. This reduction happens slowly, as the atomic arrangements may shift or experience slight disruptions over long periods. Such changes in energy density reflect the delicate balance of forces at play within the material. Understanding this aspect leads one to appreciate the intricate dynamics occurring at the atomic level. The harmonious order that once defined the magnet may begin to evolve, softly transitioning into a new state. This gentle change embodies the essence of magnetism, inviting exploration into the underlying patterns of the materials themselves, all while maintaining a tranquil energy within their forms. The quiet journey through time and structure continues, ever so thoughtfully. In the serene depths of aquatic environments, certain microorganisms navigate their surroundings with a remarkable ability. Magnetotactic bacteria are a fascinating example of this adaptability. Within their tiny structures, these bacteria harbor minute magnetic particles known as magnetosomes. These magnetosomes act like natural compasses, allowing the bacteria to align themselves with the Earth's magnetic field. Each magnetosome is a delicate assembly encapsulating magnetite or greigite crystals that serve as the tiny magnets in the bacterium's microscopic world. This alignment helps the microorganisms find their way through the water, guiding them toward the conditions that are optimal for their growth and survival. The presence of these tiny magnetic particles adds a layer of complexity to their internal organization, revealing how life can thrive in diverse environments. Over time, as these bacteria engage with their surroundings, the magnetosomes maintain their balance between stability and mobility, quietly supporting the bacteria's journey. The gentle interactions between the magnetotactic bacteria and their environment create a subtle dance of orientation, rooted in the simple yet profound relationship with the Earth's magnetic field. This ongoing relationship continues to evolve, inviting deeper exploration into the unseen forces shaping life in the water's embrace. In the world of metals, there exists a subtle phenomenon known as magnetostriction. This occurs when certain materials experience a change in size or shape in response to a magnetic field. As a magnetic field is applied, the atoms within the material rearrange ever so slightly, leading to these minute alterations in form. The effect can be quite small, yet it encapsulates the delicate balance of forces at play within the structure of the metal. The atoms are arranged in a precise lattice, and when influenced by a magnetic field, they resonate in harmony, shifting to discover a new equilibrium. This transformation happens at a scale that is difficult to perceive with the naked eye, yet it reflects the intricate nature of atomic interactions. Each movement contributes to the overall response, demonstrating a profound connection between magnetism and matter. As the external magnetic influence wanes, the material will return to its original size and shape, restoring its familiar form. This cycle of change and return is a fundamental aspect of magnetostriction, hinting at the unseen forces that govern the behavior of metals. In this gentle dance of atoms, the relationship between magnetism and the metallic world unfolds quietly, inviting contemplation of the intricate balance that exists within. As these interactions continue, the universe of materials reveals its subtle complexity, ready to be explored further in quiet reflection. Deep within the realm of atomic structure, a captivating process occurs, known as magnetic resonance. This phenomenon arises when atomic nuclei, when placed in a magnetic field, experience shifts in their energy states. These nuclei, which are composed of protons and neutrons, have specific energy levels that they occupy. When exposed to a magnetic environment, they can absorb energy and transition to higher energy states, momentarily altering their natural locations. The magnetic field exerts a gentle pull, aligning the nuclei in a way that prepares them for these transitions. As the magnetic field interacts with the atoms, it induces a quiet dance of energy where the nuclei begin to resonate at particular frequencies. When the external magnetic influence is adjusted or removed, these nuclei release their stored energy, returning to their lower energy states. This release of energy can create signals, providing a glimpse into the internal structure of the material. While this process is often employed in various fields, it remains fundamentally a reflection of the intricate relationship between magnetism and the energy that binds atomic nuclei. The subtle shifts and gentle transitions highlight the harmony at play within the heart of matter, an ongoing dance that invites further curiosity. As this interplay of magnetism and energy continues in its soft cadence, a serene understanding of the atomic world unfolds, allowing for quiet contemplation of the complexities hidden within. The journey through this hidden landscape remains inviting, ready to reveal more in its slow, persistent rhythm. Magnetic fields, quietly generated by celestial bodies such as Earth, possess a remarkable ability to endure over millions of years. Within the core of our planet, the movement of molten iron creates a dynamic flow that gives rise to this magnetic field. As these molten materials circulate, they generate electric currents, which in turn produce a magnetic force. This magnetic field envelops the Earth, extending far into space and creating a protective shield around our planet. The contours of this enduring magnetism shift subtly over time, yet its essence remains constant, guarding the planet against cosmic rays and solar winds. This softly pulsating field acts as a barrier, deflecting charged particles that travel through space, preserving the delicate balance that sustains life. As the magnetic field persists, it records the intricate history of the Earth's geological activity. Changes in the magnetic polarity, known as geomagnetic reversals, occur on a grand timescale, revealing the planet's dynamic nature. This magnetic environment continues to evolve in measured ways, demonstrating the stability and resilience of the forces at play deep within. With each moment, this gentle interplay between magnetic energy and celestial phenomena unfolds, echoing a calm continuity that invites further exploration. The presence of this enduring shield remains a serene testament to the lasting nature of earthly forces. Coral reefs, those intricate structures of vibrant colors and diverse life, harbor tiny magnetic particles within their hard limestone formations. As these reefs grow, layer by layer, the alignment of these particles becomes attuned to the Earth's magnetic field. This gentle interaction captures the magnetic orientation as it shifts over time, preserving a record of changes in the planet's magnetic behavior. Each increment of growth in the reef mirrors the passage of decades, forming a historical archive beneath the sea. As the coral expands outward and upward, the embedded magnetic particles align themselves according to the prevailing magnetic forces. This process occurs quietly, almost imperceptibly, while surrounding marine life thrives in the sheltering arms of the coral. The rich tapestry of the reef encapsulates the subtle nuances of Earth's magnetic fluctuations. Over countless years, this silent documentation unfolds, revealing shifts that connect to the planet's dynamic processes. These magnetic alignments tell a story of resilience, continuity, and subtle transformation, allowing one to ponder the intricate layers of nature's history, resting gently in the depths of the ocean, ready to be observed. The Earth's magnetic intensity is not constant. It ebbs and flows, introducing subtle shifts that span centuries. These variations occur gradually, creating a dynamic environment where the magnetic field can weaken or strengthen. Over long periods, this change influences the delicate balance of natural forces. Animals, particularly those that rely on Earth's magnetic field for navigation, can feel the effects of these fluctuations. Birds, for instance, depend on the magnetic cues as they journey across vast distances. Changes in magnetic intensity may alter their navigational pathways in ways that are quiet and seamless, yet profound. Within this context, the Earth continues its slow dance of magnetic transformation, affecting not only creatures seen in the skies, but also those living in the depths of the oceans and on land. Over time, these gradual shifts weave a narrative that is almost imperceptible, yet it forms the backdrop of life itself. Amid this quiet, unending cycle, the planet remains a vast, interconnected system, continually adapting, sustained in a peaceful balance, ready to unfold its next chapter. Permanent magnets possess a remarkable stability that allows them to retain their magnetism for extended periods. This enduring quality arises from the unique arrangement of their internal structure. Inside a permanent magnet, the atoms are intricately bonded, creating a harmonious configuration that keeps the magnetic domains aligned. Each magnetic domain acts like a tiny magnet, and when these domains point in the same direction, they generate a strong and consistent magnetic field. The force of attraction or repulsion hinges on this internal order. Because the atomic bonds hold the domains firmly in place, shifting these orientations becomes a challenging task. Over time, this arrangement remains largely unchanged, allowing permanent magnets to maintain their strength for many years. Even with external influences, such as temperature changes or physical impacts, these magnets exhibit a resilient nature. Their steadfastness can be calming, representing a stable presence in the ever-changing world around us. In this gentle embrace of stability, the dance of atoms continues quietly, ensuring that the magnetism remains poised and ready, flowing from one moment to the next. Superconductors embody a fascinating property known for their ability to conduct electricity without any resistance. When cooled to remarkably low temperatures, they create a unique state where electrical current can flow freely. In this tranquil environment, the currents can persist infinitely, moving along the conductive pathways without losing energy. This absence of resistance means that the electrons within the superconductor glide smoothly, unimpeded by the atomic structure. The normal obstacles that typically slow down electric flow, such as impurities or lattice vibrations, become irrelevant in this special state. As a result, under optimal conditions, a superconducting loop can sustain a current endlessly, almost as if time stands still for the energy within. These steady currents evoke a serene quality, embodying a perfect harmony within the material. The precise arrangement of atoms which allows this phenomenon to occur remains quietly stable, providing a backdrop for the continual flow of electrons. This delicate balance invites a sense of calm, lingering in the stillness of the conductive pathways, ready to unveil more of its tranquil mysteries as we explore further. Ferromagnetic materials possess an intriguing characteristic, rooted in the alignment of their magnetic domains. Each domain acts like a tiny magnet, with its own magnetic field, quietly oriented in various directions within the material. When these domains align consistently, the material itself becomes magnetized, exhibiting a unified magnetic field that can be strong and stable. As the temperature of a ferromagnetic substance rises, an interesting change occurs. The added energy introduces a gentle agitation among the atoms, which in turn causes these domains to become disordered. This shift in alignment reflects a transition from a state of order to one of chaos, subtly affecting the overall magnetic properties. When the domains are disordered, the material's ability to produce a strong magnetic field diminishes. The once cohesive alignment dissolves into a more random arrangement as the thermal energy disrupts their peaceful coexistence. This delicate balance between order and disorder illustrates the interplay of energy within the material, inviting reflection on the silent shifts that take place at a microscopic level. Such transformations linger in the air, gently hinting at the deeper hidden dynamics that await discovery as this exploration continues onward. The arrangement of atoms within magnetic materials plays a crucial role in sustaining their magnetic properties over time. In these materials, atoms are closely packed together, forming a resilient internal structure that fosters consistency. This compact arrangement allows for strong interactions between individual atoms, which contributes to the stable magnetic fields created within the material. The density of atoms creates an environment where electronic spins can align effectively, enhancing the material's magnetic strength. This alignment is not merely a temporary state, it becomes ingrained, allowing the material to maintain its magnetic characteristics for many years, even in the absence of external influences. As time flows gently on, the internal structure remains remarkably robust. Each atom, positioned thoughtfully within this network, plays its part in preserving the collective magnetic identity of the material. Such stability quietly underscores the beauty of the natural order at the atomic level, where harmonious relationships sustain lasting properties. This sense of continuity within the fabric of magnetic materials hints at the deeper secrets yet to be uncovered, inviting curiosity to linger softly. The Earth's magnetic field is a dynamic and evolving entity, exhibiting an intriguing pattern of polarity reversals. These changes occur roughly every 200,000 to 300,000 years, a span that underscores the slow and rhythmic nature of our planet's geological processes. During these reversals, the magnetic north and south poles switch places, creating a fascinating shift in the magnetic landscape. As the Earth's magnetic field transitions, the process unfolds gradually, with the shift occurring over thousands of years. This gentle movement allows the Earth's magnetic characteristics to adapt smoothly, even as the two poles exchange their positions. The internal structure of the Earth, with its molten iron core, plays a vital role in generating this magnetic field, sustaining the flow of magnetic forces. In this calm and slow transition, the alignment of atomic structures within the core shifts subtly, impacting the prevailing magnetic orientation. Each reversal leaves behind a trace, recorded in the layers of rock and sediment, preserving the history of Earth's magnetic past. This quiet change is a reminder of the constant motion beneath the surface, gently weaving a tapestry of time, yet still inviting exploration into its mysteries. The slow, steady movement of tectonic plates beneath the Earth's surface contributes to the ever-changing nature of magnetic fields. Over millions of years, these plates drift apart, collide, or slide past one another, creating subtle transformations in the surrounding environment. As they shift, the rocks that comprise the crust respond to these movements, which in turn influences their magnetic properties. When tectonic plates interact, new minerals can form, and existing rocks may become altered. These changes can enhance or diminish the magnetism within the rocks. For example, when molten rock cools at the edges of tectonic boundaries, it can lock in the prevailing magnetic orientation at the time of its solidification. This process captures a moment of the Earth's magnetic history, effectively creating a record of the planet's ongoing geological dance. As layers of rock accumulate over time, they embody a chronicle of these shifts, bearing witness to the slow yet significant interplay of movement beneath. Each slight change in position contributes a new detail to the narrative of Earth's history, seamlessly reflecting the dynamic and interconnected nature of its geology. This gentle unfolding continues to remind us of the subtle complexities resting just beneath our feet as the planet slowly evolves. Magnetic materials possess a unique ability to retain their magnetism over extended periods, a characteristic known as remanence. This property allows them to hold on to their magnetic orientation even when external influences, such as other magnetic fields, are removed. As magnetic materials undergo changes and align their internal structures, they can capture and maintain a specific magnetic state that reflects past conditions. This retention of magnetism is shaped by the arrangement of atoms within the material, which can lock into a stable configuration. Over time, this integrity remains, preserving the magnetic information for future reference. The stability of remanent magnetism plays a fundamental role in natural systems, like the geological records found in ancient rock formations. Each layer of magnetic alignment tells a story of the Earth's history, encapsulating the shifting magnetic fields over millions of years. This enduring capacity is mirrored in various magnetic materials used in technology, where they create a form of memory. The long-lasting nature of remanence ensures that data can be stored reliably, echoing a process so ancient and persistent it connects the modern age to the deep past. The quiet interplay of magnetism within materials continues steadily, allowing for a profound connection between the Earth's past and present, and this fascinating phenomenon carries on, waiting to unveil more of its secrets. The strength of a magnet is not a fixed quality. it can diminish gradually over time. This decline in magnetic strength occurs in response to various influences. High temperatures can disrupt the delicate arrangements of atoms within the material, altering the alignment that contributes to its magnetic properties. When exposed to heat, the internal structure may loosen, causing a gradual loss of magnetic energy. Similarly, physical shocks, whether from a sudden impact or harsh handling, can also disturb the stability of the magnetic field. These disruptions can move the atoms away from their aligned positions, further contributing to the weakening process. Over time, these changes accumulate, leading to a slow, gentle fade in the magnet's potency. Even in the most stable magnets, this gradual decline reveals the fragility of their magnetic hold. Such subtle transformations occur quietly, yet they speak to the dynamic nature of matter itself. The underlying structure remains, constantly responding to the environment while maintaining its existence, evolving softly over the ages. A magnet, in its essence, continues to embody the calm interplay of forces, quietly embodying the natural rhythms of change. Magnetostriction reveals the subtle yet fascinating behavior of magnetic materials under the influence of magnetization. When a magnetic material is magnetized, it undergoes a slight change in shape or dimensions. This transformation occurs because the alignment of magnetic domains, which are tiny regions within the material, adjusts in response to the magnetic field. Each domain, when aligned, exerts internal pressure, leading to a change in size or form. This process can be very gentle, often imperceptible to the human eye, yet it plays a crucial role in the material's characteristics. The structure of the material shifts ever so slightly, creating internal tension. The degree of magnetostriction can vary widely among different magnetic materials, reflecting their unique atomic arrangements and bonding behaviors. As the material interacts with its magnetic environment, these small changes can accumulate, revealing the deeper interactions at play within the atomic structure. This continuous adaptation allows the material to exhibit dynamic responses, embodying the quiet dance of the forces that shape its existence. The tranquility of this process highlights the balance within, reflecting the calm complexity found in nature. Each tiny shift holds a world of internal activity, subtly influencing the material's character. This gentle interplay continues, revealing a rich tapestry of interactions, ready to unfold further into the quiet night. The magnetic output of the sun operates through cycles that unfold over many years, revealing a rhythm that subtly influences the Earth's climate. This solar magnetic activity ebbs and flows in cycles, primarily the 11-year solar cycle, where the sun's magnetic field becomes more active, producing sunspots and solar flares. During peak activity in the cycle, the sun emits greater amounts of solar energy, sending waves of radiation across the vastness of space. These variations in solar output can impact the Earth's atmosphere, creating delicate shifts in temperature and weather patterns over decadal and centennial timescales. This intricate connection means that periods of heightened solar activity can correlate with warmer climate phases, while quieter phases may bring cooler conditions. Over time, these patterns weave together, shaping the climate in ways that can sometimes be measured in generations. The sun, in its ceaseless glow, subtly interacts with the Earth's environment, guiding the dance of weather rhythms and long-term climate shifts. This complex interplay suggests a harmonious cycle, where the gentle fluctuations in solar energy cast a warming or cooling influence upon our planet, inviting reflection on the greater cosmic conditions that cradle life. The threads of solar activity and climate continue to unfold, quietly influencing the world around us in a steady, ongoing embrace. Magnetism plays a crucial role in the intricate dance of charged particles. Within electric fields, these particles move in response to the forces around them, guided by the invisible hand of magnetic fields. This interplay creates pathways of motion as they spiral and drift in connection with their surroundings. When gravity is introduced to this scenario, the behavior of charged particles continues to evolve. Gravity, a gentle force that pulls objects toward one another, interacts with the paths set by magnetic fields. As these particles navigate the tension between magnetic guidance and gravitational pull, their trajectories become influenced over time, creating a delicate balance among these forces. This relationship forms a continuous cycle where the movements of particles can reflect changes in their environment. Over time, these interactions shape a larger picture of how energy and matter respond under various conditions, embracing the complexity of the universe in a soft, steady rhythm. Each moment of motion contributes to a greater whole, weaving an intricate tapestry of interconnected forces that guide the behavior of charged particles. The dance of magnetism and gravity continues to unfold within this vast cosmic web, inviting quiet contemplation of the elegant simplicity present in the natural world. The internal structure of a magnet is a delicate arrangement of atoms, positioned in specific orientations that define its magnetic properties. When stress is introduced to the magnet, whether from external forces or changes in temperature, this arrangement can shift subtly. Such shifts lead to variations in the stability of the magnetic field. As the atoms adjust, they influence the alignment and interactions with their neighboring atoms. A stable configuration generates a magnetic field that can persist over time, forming a consistent pattern of attraction and repulsion. This stability allows the magnet to maintain its properties even as the surrounding environment changes gradually. The interplay of atomic arrangements and internal stresses ensures that the magnet does not easily lose its strength or character. Over longer periods, these internal factors work quietly, preserving the magnet's essence within an unchanging framework. Consequently, the interactions and alignments of atoms create a harmonious balance that enriches the nature of magnetism. Each detail of their arrangement contributes to a broader understanding of how such systems function and allows us to appreciate the gentle complexity contained within a magnet. The dance of these atoms continues, softly revealing the rich inner world of magnetic properties, poised in stillness, ready to be explored further. Within the core of permanent magnets, temperature plays an essential role in preserving their magnetic qualities. At lower temperatures, the atomic interactions are more tightly held together, creating a serene environment that allows the magnetic domains to maintain their precise alignments. These domains, clusters of atoms with aligned magnetic moments, thrive in this cooler state where the energy flows gently, keeping them stable. When temperatures rise, however, the gentle balance can be disrupted. The increased energy can lead to chaotic movements among the atoms, causing the magnetic domains to misalign. This misalignment can weaken the overall magnetic effect, resulting in a gradual loss of magnetism. The energy shifts allow for more randomness, disrupting the order established at lower temperatures. As the surroundings cool again, the internal structure has the opportunity to realign. The magnetic domains begin to settle back into their organized patterns, restoring the magnet's strength gently and quietly. The temperature acts as a guiding hand, softly influencing this delicate dance of atoms, preserving the magnet's essence over time, patiently awaiting the return of the calm. Igneous rocks, formed from molten magma that cools and solidifies, begin to reveal their magnetic properties during a slow, tranquil cooling process. As the magma gradually loses its heat over millions of years, the atoms within start to arrange themselves in orderly magnetic patterns. This calm and measured cooling allows the magnetic minerals within the rock to lock into place, capturing the Earth's magnetic field at the time of solidification. Each igneous rock essentially becomes a time capsule, preserving a record of the Earth's magnetic environment from the moment it formed. The aligned magnetic domains within these rocks serve as indicators of the planet's past magnetic orientation. They provide hints about how the magnetic field has shifted and changed over eons, offering geologists a way to piece together the history of the Earth. With every layer of magma that cools, another chapter is added to this silent story. Over countless years, these rocks accumulate evidence, building layers that speak to geological processes and magnetic shifts. Each piece contributes to the understanding of the Earth's intricate history, quietly awaiting discovery in a world where time stretches gently and endlessly, hinting at the rich tapestry of the planet's past. Magnetic fields, vast and often invisible, influence more than just metallic objects. When light from distant stars travels across the universe, it sometimes encounters these powerful fields. The interaction between the magnetic forces and the path of light can cause the light to bend, a subtle but fascinating effect. As the light journeys through space, it may pass near massive cosmic entities such as neutron stars or black holes, where magnetic fields are incredibly strong. In these environments, the light is not merely a straightforward beam. Instead, it dances gently, curving slightly as it navigates the gravitational and magnetic influences. This bending alters the appearance of the stars, creating a distorted view that reveals a deeper connection between light and the cosmic landscape. The light that reaches our eyes or telescopes carries stories of these encounters, telling us about the unseen forces that shape the fabric of space. Every time light bends due to a magnetic field, it adds a layer of complexity to our understanding of the universe, hinting at the intricate interplay between light, gravity, and magnetism. These quiet shifts in light's journey remind us of the mysteries that lie beyond our immediate perception, wrapped in a veil of cosmic wonder. Each bending path invites a calm contemplation of the expansive universe, ready to unfold further tales and secrets in its vastness. Magnets are fascinating objects, primarily composed of metals such as iron, nickel, and cobalt. These materials possess a unique atomic structure that enables them to exhibit magnetism. Within each magnet, there are tiny regions known as magnetic domains. Each domain acts like a mini magnet, having its own north and south pole. In most materials, these domains point in random directions, canceling each other out and resulting in no overall magnetism. However, in magnetic materials, many of these domains align in the same direction. This alignment creates a unified magnetic field, giving the magnet its distinctive properties. The strength of a magnet directly relates to how many domains are aligned and how well they maintain that orientation. When these domains stay aligned, the magnetic influence extends outward, quietly interacting with nearby objects. As one observes a magnet, it becomes clear that the calm, consistent alignment of these domains is what allows magnetism to emerge. Even in the stillness of the night, the structures within a magnet remain active, harmoniously maintaining their positions. Each magnetic field represents a delicate balance of forces, inviting contemplation of the unseen connections that weave through the materials around us, patiently waiting to reveal their nature in time. Certain microorganisms experience subtle changes when exposed to magnetic fields over extended periods. Within these tiny life forms, minute processes unfold, revealing a fascinating interaction between the magnetic environment and biological forces. As they adapt to their surroundings, the growth patterns of these microorganisms may shift, reflecting a quiet responsiveness to the unseen magnetic influence. The long-term exposure can lead to evolutionary adaptations, where tiny adjustments occur at the cellular level. These changes often enhance survival within varying magnetic conditions, suggesting that magnetism plays a role in the natural selection process for these organisms. The alignment of cellular structures can subtly adjust, allowing for a different orientation within a magnetic field, which may affect their ability to navigate or thrive. Like a gentle rhythm, these adaptations occur slowly over generations, quietly weaving magnetism into the fabric of their existence. Observing this interplay encourages a sense of wonder about the intricate connections between magnetic phenomena and life in its smallest forms. Each tiny microorganism dances softly within its world, responding to influences that shape its very being, ever ready to continue its journey through the mysteries of existence. Magnets, though often thought to possess enduring strength, experience a gentle fading over time. The process is gradual, like leaves turning color in the autumn. Permanent magnets can lose about 1% of their magnetism every decade, a quiet shift that occurs especially when they are exposed to higher temperatures or external magnetic fields. Within their internal structure, the arrangement of atoms plays a key role. These tiny particles, constantly in motion, can become less aligned as conditions change. Elevated temperatures may disrupt their order, leading to a soft decline in magnetic force. And similarly, proximity to other magnets can influence their own magnetic properties, gently nudging them toward a decrease in strength. This slow diminishment unfolds quietly and barely perceptibly, allowing magnets to maintain their usefulness for long periods. Even as their strength wanes, they continue to reveal the intricate balance of forces within their core. This enduring yet delicate existence reminds us of the subtle ways that time and environment shape the essence of even the most solid-seeming objects, inviting curiosity about their ongoing story. Superconductors are fascinating materials that reveal remarkable behavior when cooled to very low temperatures. One of the most intriguing characteristics they display is known as the Meissner effect. As superconductors reach their critical temperature, they start to expel magnetic fields from their interior, creating a unique interaction with their environment. This phenomenon allows them to repel magnetic fields, which not only showcases the hidden energy within these materials, but also leads to striking effects like levitation. In this state, a superconductor can float above a magnet, defying the usual gravitational pull. The expulsion of the magnetic field means that the superconductor creates its own magnetic field that pushes against the external one. This interaction is delicate and fascinating as it illustrates a perfect balance between opposing forces. The internal structure of superconductors contributes to this behavior, with electrons moving in a coordinated manner that enhances this repulsion. This quiet yet powerful display of energy offers a glimpse into the complexity and beauty of nature's physical principles, inviting peaceful reflection on the mysteries that surround us, ready to be explored further in the mind's gentle wanderings. The Earth's magnetic field is a dynamic presence, quietly fluctuating over vast timescales. Over thousands of years, this field undergoes cycles of intensity, with variations that create what are known as geomagnetic minimums. During these periods, the magnetic field can weaken significantly, leading to a softening of its protective embrace around our planet. As the field weakens, the environment surrounding Earth experiences changes in radiation exposure. The cosmic rays and solar particles that travel through space are influenced by the strength of this magnetic barrier. When the geomagnetic field is at its lowest, these energetic particles can penetrate more easily into the atmosphere, subtly altering the conditions of the environment. This natural rhythm of the magnetic field flows gently like a tide, its fluctuations sometimes unnoticed against the backdrop of daily life. Earth's core, composed of molten iron and nickel, contributes to these variations, as the movement within creates currents that shape the magnetic environment over thousands of years. The interconnectedness of these processes is a quiet reminder of the living planet we inhabit, where forces at play are constant yet often unseen. The slow dance of the magnetic field continues, inviting further exploration into its mysteries, allowing thoughts to drift softly into rest. The magnetic poles of the Earth are not fixed in place. They gently shift and wander over time, influenced by the dynamics of the core beneath our feet. At the heart of our planet, intense heat and pressure create motion in the molten iron and nickel. This movement generates electric currents, which in turn shape the magnetic field that envelops the Earth. As the core changes, so too do the magnetic poles, slowly drifting from their original positions. This gradual alteration can take thousands of years, marking an ongoing dance of the Earth's internal forces. Occasionally, this process reaches a remarkable point where the magnetic field undergoes a complete reversal, reversing the locations of the magnetic north and south. Such an event is not abrupt, but a gradual transition that unfolds over extended periods, a natural evolution in the planet's geophysical behavior. During these shifts, the Earth's magnetic field exhibits a temporary weakening, allowing a subtle interplay between cosmic influences and the planet itself. This long-term transformation is a quiet, continual reminder of the dynamic forces that shape our world. The gentle movement of the magnetic poles continues, sending soft ripples through the fabric of time and inviting an exploration of the mysteries that lie beneath the surface, ready to drift into peaceful contemplation. Cosmic rays, high-energy particles that travel through space, interact with our planet in complex ways. Long-term observations show that their intensity is not constant, but rather varies with the magnetic activity of the sun. Each cycle of solar magnetic activity unfolds over decades, with the sun entering phases of increased and decreased energy. During periods of heightened solar activity, the magnetic field generated by the sun acts as a shield, diverting many cosmic rays away from Earth. This natural shield can create a quieter environment in our atmosphere. Conversely, during times of lower solar activity, this protective barrier weakens, allowing a greater number of cosmic rays to reach the Earth's surface. As these high-energy particles collide with atoms in the atmosphere, they create secondary particles, which can also impact our environment. The gentle rhythm of cosmic ray intensity in relation to solar magnetic cycles offers a glimpse into the dynamic interactions of forces beyond our planet. These long-term fluctuations provide valuable understanding of our universe, highlighting the interconnectedness of cosmic events and our Earth. As the sun continues its cycles, so too does the quiet presence of cosmic rays, weaving a delicate tapestry of time and space. This interplay continues to unfold, inviting further exploration into the realms above us, eternally drifting across the vastness of the cosmos. Magnetic minerals found within various various types of rocks possess a fascinating property. Over the course of thousands of years, these minerals can record the Earth's magnetic field direction like a natural diary. As new layers of minerals form, they align themselves with the prevailing magnetic field at that moment. This delicate alignment captures a snapshot of the Earth's magnetism, preserving it for ages to come. When rocks undergo changes through natural processes such as erosion or tectonic activity, these magnetic signatures remain embedded within them. Scientists can extract and analyze these minerals, allowing them to read the history of the Earth's magnetic field. Insights gained from this analysis reveal the shifting nature of the Earth's magnetism over time, illustrating a dynamic planet that has experienced fluctuations in its magnetic orientation. This quiet recording of Earth's magnetic field creates a continuous history that spans epochs, offering a glimpse into the deep past. Each discovery enhances our understanding of how the planet has changed and evolved over vast periods. The subtle interplay of magnetic forces and geological time continues quietly beneath our feet, waiting to be unlocked as the Earth ever so gently tells its story through the layers of stone and time. The Milankovitch cycles represent a slow but profound dance of Earth's movements over tens of thousands to hundreds of thousands of years. These cycles are generated by gradual shifts in the shape of Earth's orbit around the Sun and variations in its axial tilt. Such changes are subtle, yet significant, gently altering the way sunlight reaches our planet. As these patterns unfold, they create fluctuations in climate, permitting long-term variations in temperature and weather conditions. These alterations in orbit and tilt don't only influence climate, but may also impact the strength and distribution of Earth's magnetic field. The magnetic field, an ever-present force surrounding our planet, can be influenced by these climatic changes, reverberating through layers of the Earth as the cycles progress. Over time, these fluctuations contribute to the complex relationship between climate and magnetism, shaping patterns in the environment. The intricate interplay of these cycles forms a delicate balance that affects various processes deep within the Earth. Each cycle builds upon the last, forming an enduring rhythm that stretches through geological time. As these whispering movements continue, they serve as a reminder of the vast timescales at play in the natural world, quietly guiding the Earth through its journey in space. At temperatures approaching absolute zero, magnetic materials enter a unique state known as superconductivity. In this realm of frigid conditions, the typical resistance that materials exhibit to electric current disappears entirely. Within this state, these materials can carry an electric current indefinitely, flowing smoothly without any loss of energy. The transition to superconductivity occurs as the thermal vibrations of atoms diminish, allowing electrons to pair up in a way that facilitates their movement through the material without encountering obstacles. In fact, this harmonious flow creates conditions where energy can travel unimpeded, a remarkable adjustment in the behavior of matter. The phenomenon reflects a deep connection between temperature, magnetic properties, and electrical behavior. In these chilly environments, the interactions between particles shift dramatically, revealing pathways that are otherwise hidden at higher temperatures. As the subtle balance of energy and motion calms, a fascinating dance unfolds, one that highlights the wonders of the physical world in the far reaches of temperature. The simplicity and elegance of superconductivity linger gently in the air, inviting contemplation as these materials hold the potential for transformation within the silent framework of the universe. In certain rare magnetic materials, there exists an intriguing phenomenon known as magnetic monopoles. Under specific theoretical conditions, these materials can exhibit isolated magnetic charges that function as singular north or south poles, contrasting with the common understanding of magnets that always have both a north and a south pole. When examined closely, these monopoles behave uniquely, existing in a state where the typical paired nature of magnetism is altered. Their presence suggests that the fundamental nature of magnetic fields can be more complex than previously thought. Within these materials, the arrangement of atoms and their magnetic spins may create the conditions necessary for these isolated poles to manifest. As the environment stabilizes and the interactions among particles adjust, the magnetic monopoles appear, providing a glimpse into the nuanced behavior of matter on a fundamental level. This quiet emergence captivates the imagination, as the existence of magnetic monopoles hints at a deeper layer of understanding in the realm of magnetism. Each isolated charge dances gently in its own space, quietly revealing the mysteries of magnetic properties, existing serenely in the fabric of the universe, where simple yet profound phenomena unfold in a tranquil embrace. The efficiency of magnetic levitation systems, while fascinating, is bound by the inherent strength of the magnetic field involved. In these systems, forces arise from the interactions of magnets, creating a phenomenon that enables objects to float gently above a surface, seemingly defying gravity. The nature of this levitation is dictated by the type of materials used, such as superconductors or permanent magnets. Superconductors have the ability to conduct electricity without resistance and can generate strong magnetic fields, enhancing the effective levitation. Their behavior changes dramatically at low temperatures, allowing them to maintain a stable magnetic field that is crucial for achieving higher levitation efficiency. Conversely, permanent magnets, while simpler, can offer a more limited range of magnetic strength, which constrains how much weight can be suspended. As these magnetic fields interact, variations in efficiency can occur. The strength of the magnetic field ultimately determines the balance of forces at play, contributing to the fascinating dance of levitation. This delicate balance reflects a deep interplay of physics, the consistency of magnetic properties, ensuring stability over time. Moments of stillness and graceful floating arise from these principles, a gentle reminder of how foundational forces create harmonious phenomena in the world around us. As we explore further, the nuances of these magnetic behaviors offer a serene continuation into a realm of quiet wonder. Certain materials hold their magnetic properties tightly, yet these can change dramatically with heat. This process, known as thermal demagnetization, reflects how temperature influences the structure of magnetic materials. When these substances are exposed to high temperatures, the thermal energy disrupts the orderly arrangement of their atoms. This disarray leads to a loss in their ability to maintain a stable magnetic field. As heat increases, the organized spins of electrons, which contribute to magnetism, begin to scatter and lose their alignment. This gradual disruption may lead to irreversible changes in the magnetic field, altering the behavior of the material. Once cooled, the material might no longer exhibit the same strength of magnetism, highlighting the delicate balance that temperature imposes on these physical properties. Over time, such changes can have lasting effects on a material's overall magnetic characteristics. The intimate relationship between heat and magnetism reveals a complex dance of atomic interactions, where energy flows create shifts in stability. These transformations offer a serene glimpse into the world of materials, inviting us to reflect on the gentle interactions that govern their existence. With each change, there lies a calm assurance that new patterns will continue to emerge, quietly shaping the essence of magnetic phenomena. Earth's magnetic field is far from static. It shifts gently over vast stretches of time. This continuous change is intricately linked to the formation of new oceanic crust at mid-ocean ridges. These ridges are points where tectonic plates move apart, allowing molten material from the mantle to rise to the surface. As this material cools, it solidifies into new crust, a quiet process that contributes to the gradual transformation of the planet's magnetic landscape. As molten rock cools and crystallizes, iron-rich minerals within it align with the Earth's magnetic field, imbuing the crust with its magnetic properties. Over millions of years, as tectonic plates continue to diverge, the older portions of the ocean floor move away, gradually recording changes in the magnetic field within their structure. Each layer of crust captures a snapshot of the Earth's magnetic orientation at the time of its solidification. This slow dance of creation and movement unveils the dynamic nature of Earth's magnetic field. Variations occur as the newly formed crust interacts with the ever-changing forces beneath it. With the passing eons, the magnetic field's shape evolves, marking the story of the Earth's geological activity. Each moment in this process contributes to a deeper understanding of the planet's magnetic identity, allowing an endless unfolding of natural phenomena full of quiet potential. In a tranquil setting of specific laboratory conditions, a fascinating phenomenon emerges, known as persistent magnetic levitation. This occurs when a superconductor is placed above a magnet, allowing it to float gracefully in midair. The superconductor, when cooled to exceedingly low temperatures, enters a unique state where its internal resistance to magnetic fields changes profoundly. As the magnetic field interacts with the superconductor, an effect known as the Meissner effect takes place. The material expels the magnetic field lines from its interior, creating an environment where it can hover above the magnet without touching it. This delicate balance allows for a snug fit, where the superconductor remains stably suspended, held in place by the magnet's invisible force. This state of levitation does not require energy input to maintain once initiated. The superconductor can stay afloat for long stretches of time, whispering of a quiet elegance within the physical world. The continuous interplay of magnetic fields reveals a captivating aspect of materials under specific circumstances, demonstrating the remarkable nature of their properties. Such phenomena invite wonder and curiosity, suggesting that there are always deeper layers of understanding yet to uncover, resting in a realm of peaceful possibility. Temperature plays a crucial role in the behavior of magnetic materials, deeply influencing their magnetic properties. Each material has a specific characteristic temperature known as the Curie temperature. At this critical threshold, certain materials undergo a significant transformation, losing their permanent magnetic properties. Below this temperature, they maintain a stable magnetic alignment that gives rise to strong magnetic fields. As the temperature rises and reaches the Curie point, this order begins to fade away. The internal structure of the material, which consists of atoms with spins that align in certain ways, shifts from an organized state to one of randomness. This change disrupts the uniformity of the magnetic fields, leading to a loss of magnetism. Interestingly, the Curie temperature remains relatively constant over time for each individual material, reflecting its stable atomic characteristics. As time passes and conditions remain stable, the relationship between temperature and magnetism in these materials remains reliable. The quiet workings of nature offer a serene reminder of how fundamental principles guide the behavior of physical systems, inviting further exploration into the harmonious balances found within their structure. Magnetic fields possess a remarkable range, with some capable of becoming extraordinarily strong. In specialized laboratory settings, researchers can create magnetic fields that reach impressive intensities, often soaring to around 45 teslas. This strength is astonishingly far greater than the Earth's magnetic field, which is a mere 0.00005 teslas. The structure of magnetic fields is influenced by the motion of charged particles within materials, their arrangement, and the temperature conditions that prevail during experiments. When fields are generated at such high intensities, the internal alignment of spins and charges intensifies, producing effects not observable under normal conditions. These powerful fields reflect the intricate interaction between matter and magnetism, emphasizing the fascinating dynamics within materials at varying strengths. Continuous study and experimentation allow scientists to delve deeper into the phenomena at play, revealing the complexity of magnetic forces in a manner that remains consistent over time. The gentle ebb and flow of these discoveries invites further contemplation, leading us to explore the subtleties of nature's hidden workings. Within the realm of engineered materials lies a fascinating area known as spintronics. In these materials, the spin of electrons is a key feature utilized in unique ways. Electron spin, a fundamental property of particles, can be thought of as a tiny magnet that can point in different directions. By manipulating this spin, it is possible to create processes that rely on magnetic fields rather than traditional electric currents. This shift enables the development of systems that can operate at quicker speeds, allowing for more efficient data processing. The arrangement of atoms and the interplay of spins within these materials contribute to their distinct behaviors. Over time, the stable configurations created through spin manipulation enhance the reliability of these systems. The peaceful dynamics of electron spins working in harmony create a serene backdrop for advancements. Each discovery encourages deeper exploration of the subtleties of magnetism and its potential, fostering a sense of curiosity in the silent interactions occurring at the microscopic level. Within the intricate world of certain bacteria, an extraordinary relationship with magnetic minerals unfolds. These microorganisms possess the ability to utilize tiny particles of magnetite, a form of iron, to navigate their surroundings. Each of these magnetic minerals aligns with the Earth's magnetic field, guiding the bacteria as they move through varied environments, whether in soil or water. Over long periods, as ecological conditions shift and adapt, these bacteria gradually evolve, fine-tuning their magnetic properties in response to their surroundings. Changes in temperature, nutrient availability, or the presence of other organisms can influence their magnetic systems. This delicate interplay encourages a slow transformation, reflecting the resilience and adaptability of life at the microscopic scale. As generations pass, the bacteria's navigation mechanisms become attuned to their evolving habitats, illustrating a quiet yet profound evolution of their internal structures. Each small change weaves into the larger fabric of their existence, emphasizing the calm, constant movement of nature's intricate designs. In the realm of ferromagnetic materials, a delicate balance of stability exists within the magnetic domains. These domains act like tiny magnets themselves, each possessing a specific direction of magnetization. When a strong external magnetic field is applied, these domains respond, aligning in a way that enhances the overall magnetism of the material. However, this alignment does not happen instantaneously. Once the external influence is removed, the domains do not immediately return to their original state. Instead, they may take years or even decades to fully readjust. This gradual realignment reflects the intricate relationships within the material as the internal structure slowly transforms. Various factors can affect this process, including temperature changes and local disturbances in the material. The long-term magnetic properties of these materials are therefore shaped by this slow dance of domains, emphasizing a remarkable stability. Over time, as the domains quietly shift back to their natural arrangement, they illustrate the enduring nature of magnetic phenomena within the fabric of matter, inviting an ongoing exploration of these subtle transformations. The internal structure of magnetic materials is deeply influenced by their thickness. When the material is thicker, there exists a greater number of atoms that can align themselves in the same direction. This alignment is vital for creating a strong and stable magnetic field. Each atom contributes to the collective behavior of the material, like participants in a silent chorus, joining together to produce a more pronounced magnetic effect. As these aligned atoms work in harmony, they enhance the magnetic strength of the material. In contrast, thinner materials may find it challenging to maintain this cohesion, as fewer atoms can contribute to the overall alignment. The arrangement and interactions among the atoms play a crucial role in establishing not just the immediate strength of the magnetic field, but also its long-term stability. Changes in thickness can lead to subtle variations in the magnetic properties, as the balance between alignment and disorder shifts gently. The relationship between the physical dimensions of the material and its internal strength signals an intricate dance of atoms, quietly resonating within the fabric of the magnetic world. The exploration of these properties invites lingering curiosity, seamlessly continuing the journey of discovery. The effect of pressure on materials reveals the delicate interplay within their structure. As pressure increases, some magnetic materials respond by becoming more magnetically active. This transformation can alter the internal arrangement of atoms, encouraging them to realign and enhance their collective magnetic behavior. The change does not happen abruptly. It unfolds gradually as the material adjusts to the increasing weight pressing upon it. With this added pressure, some atoms may shift from their original positions, allowing for a more uniform orientation. The result is a bolstered magnetic strength as more atoms begin to work together in a synchronized manner. Over time, this gentle modification can lead to an enduring enhancement of the material's magnetic properties. As the pressures persist, the internal dynamics continue to evolve, creating a captivating process where orientation and strength dynamically respond to external conditions. The silent adjustments within the material create a fascinating narrative of transformation, quietly unfolding, inviting further reflection as the exploration of its behavior carries on. Electromagnets create magnetic fields as a response to electric current. When electricity flows through a coil of wire, it generates a magnetic field around the wire, transforming it into a magnet. This phenomenon is fascinating in its simplicity, as the presence or absence of the current dictates the magnet's state. When the electric flow is on, the magnetic field is present, exerting a force that can attract or repel other magnetic materials nearby. This force can be relatively subtle, or it can be quite strong, depending on the amount of current that passes through the wire. When the current is turned off, the magnetic field dissipates, and the magnet's influence ceases, returning the system to its unmagnetized state. The ability to switch this magnetic effect on and off provides a remarkable fluidity in its use. In this gentle dance of electricity, the magnetism is shaped and reshaped, reflecting the rhythms of the current itself. The underlying process continues, quietly inviting further exploration of the nature of electromagnetic fields and their behavior over time. The Earth's magnetic field has a remarkable characteristic. It can reverse its polarity over time. This means that the magnetic north and south poles switch places. While this reversal occurs every few 100,000 years, the exact timing of these events can be uncertain. Scientists have gathered evidence showing that the process is not regular or predictable. During these reversals, the magnetic field does not vanish entirely. Rather, it undergoes a gradual shift. This transition can take thousands of years, during which the field may weaken and become more complex. Complicated patterns might emerge, with the poles not only flipping, but also oscillating in unexpected ways. Over these vast stretches of time, the Earth's core continues to generate the magnetic field, but its inner workings remain a mystery, contributing to the field's fluctuations. The long-term behavior of the Earth's magnetic field fascinates scientists, as it reflects the dynamic nature of our planet's interior. With each cycle of reversal, the nuances of this ancient process quietly unfold, inviting calm contemplation of the natural world and its enduring rhythms. In the vastness of space, planetary magnetic fields encounter continuous forces from cosmic rays and solar wind. These elements are composed of high-energy particles, which, when interacting with a planet's magnetic field, can disrupt its stability. This disruption affects the magnetic shield that protects the planet from radiation. Over extended periods, the influence of these energetic particles varies, creating fluctuations in the strength and orientation of the magnetic field. As the solar wind constantly streams from the sun and cosmic rays travel through the cosmos, they pose challenges to the magnetic architectures of planets. Some fields may grow weaker or become more erratic, impacting how effectively they can deflect these particles. Such shifts in magnetic stability reveal a complex interplay within planetary systems, illustrating how external forces shape their internal structures. Despite these challenges, the dance of particles continues, reflecting the dynamic nature of our universe. Each moment unfolds with a gentle rhythm as cosmic elements whisper through the silence of space, leaving room for further exploration and understanding. Certain materials, particularly those rich in iron, have a unique response to magnetic fields. When exposed for an extended time to a strong magnetic field, these materials can become magnetized, acquiring a lasting magnetic property. This gradual change occurs as the alignment of tiny magnetic domains within the material shifts. Each magnetic domain acts like a small magnet itself, and in their unmagnetized state, they point in random directions, canceling each other out. Prolonged exposure to a magnetic field encourages many of these domains to align in the same direction, creating an overall magnetic effect that persists even after the external field is removed. This change does not happen instantly, it unfolds slowly, reflecting the gentle influence of the magnetic field over time. The process illustrates an intriguing aspect of material behavior, revealing how a seemingly simple relationship can lead to a more complex state. As these materials settle into their new magnetic identities, they quietly persist in their micro-alterations, awaiting the next moment of interaction in a constantly changing world. The Earth functions as a vast magnet, largely due to the movements within its core. This core consists of a molten outer layer and a solid inner region, both rich in iron and nickel. As these materials shift and flow, they generate a magnetic field that extends far out into space. This field is not static, it constantly ebbs and flows, influenced by the dynamic activity of the Earth's interior. The magnetic field envelops the planet, forming what is known as the magnetosphere. This protective shell is crucial as it shields the Earth from the sun's solar winds, streams of charged particles that could otherwise strip away layers of the atmosphere. By deflecting these particles, the magnetic field enables a stable environment for life to flourish. This relationship between the Earth's core and its magnetic field creates a harmonious balance, reflected in the planet's steady rotation and geological processes. Beneath the surface, this silent, powerful magnet persists, continuously influencing the world around, shaping conditions in ways that remain subtly woven into the fabric of existence. Planetary magnetic fields, such as those of Jupiter and Saturn, are fascinating structures that reveal much about their internal dynamics. These massive planets possess powerful magnetic fields that remain stable over long periods, providing a sense of consistency in their expansive atmospheres. However, beneath this stability, dynamic processes are continually at work, often hidden from view. Deep within these gas giants, a complex interplay of swirling metallic hydrogen generates magnetic fields through an effect known as the dynamo process. Over millions of years, this activity can lead to variations in the strength and orientation of the magnetic fields. Periodically, these shifts occur, altering the magnetic landscape, although they remain governed by the same underlying mechanisms. Such changes occur over extensive time spans, creating patterns that can be traced through the ages. The cycles of these shifts speak to the vibrant life of a planet's interior, where powerful forces are always in motion. With each turn of time, magnetic fields adapt and evolve, revealing the intricate balance of energy that defines these distant worlds. As they breathe and transform, they remain an essential part of the cosmic dance, a calm rhythm of existence that continues on, unwavering yet ever-changing. Permanent magnets, such as those made from neodymium, are remarkable for their ability to maintain a consistent magnetic field. However, this enduring quality is sensitive to temperature. Each type of magnet has a specific threshold known as the Curie point, which signifies the temperature beyond which it begins to lose its magnetism. For neodymium, this critical temperature is approximately 300 degrees Celsius. As the temperature rises, the orderly arrangement of the magnetic domains within the material becomes disrupted. These tiny regions, each acting like a miniature magnet, align in a way that produces a cohesive magnetic field. When the temperature exceeds the Curie point, this alignment breaks down. The thermal energy causes the magnetic domains to randomize, weakening the overall magnetic effect. In this state, the magnet no longer possesses its prior strength, revealing how delicate the balance is between temperature and magnetism. The transition reflects the intricate relationship between heat and magnetic properties, a dance of energy that governs the behavior of materials deep within their atomic structures. As time continues its steady march, these processes unfold, showcasing the subtle beauty of the physical world around us. Over the last century and a half, the strength of Earth's magnetic field has quietly diminished by around 10%, a change that unfolds gradually over time. This gentle weakening occurs as the molten iron and nickel within the Earth's outer core moves and shifts, creating currents that generate the magnetic field we experience on the surface. As these currents evolve, so too does the magnetic field, leading to fluctuations that can sometimes be difficult to detect amidst the vastness of time. The magnetic field serves as a protective barrier against cosmic radiation, a shield that safeguards our atmosphere and, by extension, life on our planet. With the field's slow retreat, the implications can ripple through navigation systems that rely on magnetic cues for orientation, quietly hinting at an unseen alteration in the environment. Such changes remind us of the dynamic nature of our planet, where forces are continually at play below the surface. This subtle dance of elements and energy flows encourages a sense of wonder about the planet's inner workings, inviting thoughts about the interconnectedness of all things within this tranquil system, allowing space to breathe and continue. Within the realm of information technology, hard disk drives quietly rely on magnetic storage to preserve data with remarkable stability. This method of storing information uses tiny magnetic regions, which can hold a charge to represent digital content. These magnetic domains are carefully positioned on the disk surface, allowing data to be written and read with precision. When conditions are stable, meaning they are protected from extreme temperatures and humidity, the integrity of this stored data can last for decades. This longevity stems from the very nature of magnetic materials, which are designed to hold their charge over extended periods. The arrangement of particles within the disk ensures that the information does not fade away easily, remaining intact for years, like whispers of the past captured in time. This reliability does not just apply to individual pieces of data, but extends to the overall structure of the magnetic disk itself. The material is carefully engineered, fostering resilience against degradation that might occur in more volatile storage methods. The balance and order of the magnetic components create a steadfast haven for countless bytes of information, resting gently until called upon, ready to unfold when the moment arrives. In this quiet coexistence lies a testament to the enduring nature of magnetic properties, inviting contemplation about the layers of complexity that exist beneath the surface. Within the vast tapestry of Earth's history, paleomagnetic studies reveal a fascinating narrative of the planet's magnetic field. This field is not a constant, rather it has experienced dramatic fluctuations over the course of millions of years. During certain periods, the magnetic field has been notably strong, wrapping the planet in a robust shield. In contrast, there have been times when it has weakened, allowing the intensity to diminish for thousands of years. These changes in strength occur through cycles, often lasting tens of thousands of years, reflecting the dynamic and ever-evolving nature of Earth's interior. As molten rock moves within the outer core, it generates currents that influence the magnetic field. This swirling motion leads to variations in field strength, causing the protective embrace to shift and adapt. Each cycle leaves an imprint on the Earth, captured in the rocks and sediments that reveal the planet's past. The subtle dance of magnetism unfolds quietly, allowing scientists to piece together the story of Earth's ever-changing character. In this peaceful rhythm, the magnetic field serves as a calm observer, adapting and evolving while maintaining its role in the planet's environmental symphony. The interplay of strength and weakness continues to echo through time, ready to share its secrets in the moments of discovery ahead. The Earth's magnetic field exists in a delicate balance, responding to various influences from beyond its own depths. Among these influences is solar activity, which brings about intriguing changes in the magnetic field structure. When the sun emits bursts of energy and charged particles, this interaction can lead to temporary disturbances known as geomagnetic storms. During these storms, the magnetic field experiences fluctuations and shifts, creating an environment of dynamic motion. These events are not permanent. They unfold with a gentle rhythm, resulting in changes that may last from minutes to days. Geomagnetic storms are a natural part of the Earth's interactions with its cosmic surroundings. As solar wind moves through space, it presses upon the magnetic field, shaping it in subtle ways. The field reacts, bending and shifting, as if responding to a gentle breeze. This play between solar forces and Earth's magnetic shield serves as a reminder of the interconnectedness of our planet and the universe beyond. As the storms rise and fall, they carry stories of cosmic energy and magnetic resonance, inviting quiet contemplation of the vast systems at work. The dance of solar energy and Earth's protective shield continues, gracefully ebbing and flowing through time. In certain regions of the Earth, the magnetic field undergoes a fascinating transformation that occurs over extensive periods. Every several 100,000 years, the magnetic poles, known as north and south, can actually reverse their positions. This means that the magnetic North Pole will become the South Pole, while the South Pole takes on the role of the North. Such reversals are gradual processes. They unfold over thousands of years, allowing the Earth to transition subtly through different configurations. During this period of change, the magnetic field might weaken, creating a less stable environment for its magnetic lines of force. Even as this occurs, the planet continues its journey around the Sun, steadfast in its rotation. These shifts are recorded in the geological layers of the Earth, embedded in the rocks that have solidified over time. Each layer holds a memory of past orientations, forming a timeline that speaks to the rhythmic nature of our planet's magnetic behavior. Through its cycles of quiet transformation, the Earth reminds us of the deep, unyielding forces at play within it, fostering an enduring connection with the natural world around us. Over the course of decades or even centuries, the mass of a magnetic object typically remains quite stable. This stability is a comforting reminder of the constancy found in the physical world. As time unfolds, however, while the weight and size of a magnetic material remain unchanged, its magnetic effectiveness may not follow suit. Factors such as corrosion or gradual physical wear can influence how well it retains its magnetic properties. The surfaces of these objects may slowly erode, exposing fresh layers to the surrounding environment. In this gentle process, the magnetic field strength can diminish, often unnoticed until a change becomes apparent. The essence of the material, though, still resides within, retaining its mass, yet evolving in its resonance. This shift in magnetic behavior occurs over long periods, capturing the intricate dance between the material world and time itself. The quiet evolution of a magnetic object is a reminder of the gradual changes that encompass all aspects of existence, reflecting a deeper rhythm in nature that continues steadily in the background, always present, always transforming, yet eternally constant. Pressure plays a subtle yet significant role in shaping the magnetic properties of materials. In certain environments, as pressure is gradually applied, the internal structure of these magnetic substances can begin to change. This influence occurs gradually as the layers of atoms adjust themselves under the weight of increased pressure. At first, the magnetic behavior may respond, perhaps becoming slightly altered in its strength or orientation. Yet, over time, these changes can find a balance, allowing the material to stabilize once again. The initial reactions to the added pressure often settle into a new state, as the atoms find their optimal arrangement under the new conditions. This process illustrates the delicate interplay between forces acting upon materials and their persistent nature. As the magnetic properties shift, they begin to create a gentle rhythm, reflecting the enduring stability within the fluctuations of the physical world. Each material, though influenced by its surroundings, retains its essence, embracing the gradual changes while remaining grounded in its core characteristics. The soft and continual dance of pressures and properties reminds us of the inherent resilience that exists within all matter, a quiet testament to the enduring ways of the universe, always moving, always adapting, yet remaining at its heart unchanged. Magnetic bearings operate through the principles of magnetism, creating a cushion of magnetic fields that allows components to levitate, reducing direct contact between surfaces. In this state, the friction that usually occurs in traditional bearings is almost entirely eliminated. With less friction comes less heat, as the mechanical parts move smoothly in their rotations. Over time, this reduction in heat and friction contributes to a more efficient system. The components can function without the wear and tear that typically arises from constant contact. The gentle interaction of the magnetic forces allows for a serene operation where parts glide effortlessly without the strain that often shortens their lifespan. Eventually, as these systems continue to run with minimal disturbance, they not only benefit from decreased energy losses, but also enjoy an extended duration of functionality. This prolonged performance is a quiet reflection of the careful balance maintained within their internal environment. Each rotation draws upon the calming stability that magnetic interaction provides, allowing the machinery within to operate with ease. This results in a peaceful harmony of structure and motion, flowing gently under the influence of magnetism, ready to embrace the next cycle of quiet activity. Over long stretches of time, the Earth's climate undergoes gradual shifts, influenced by cycles of warming and cooling. These changes affect not only the surface environment, but also the deep geological formations beneath. As temperatures and conditions alter, the movement of minerals within the Earth's crust can also change. Magnetic minerals, which are sensitive to temperature and pressure variations, begin to redistribute in response to these climatic forces. In this dynamic setting, rocks can record different magnetic patterns, capturing echoes of the Earth's historical climate through their internal structures. As these layers of rock form and solidify, they reveal a silent story of the planet's past, a history written in subtle shifts of magnetic orientation. These variations can be laid down in distinct stripes, reflecting the interplay of time and environment, a slow dance that takes place over countless years. Each layer holds a whisper of the conditions that existed when it formed, offering glimpses into bygone eras. The constant shifts within the Earth's crust help create a complex tapestry of magnetic signatures, revealing the influence of climate changes over eons. These tranquil transitions weave a rich narrative, inviting a sense of calm as the planet continues its gentle evolution. Each new layer, each magnetic record, contributes to a grand harmony that resonates far beneath the surface, endlessly turning with the pulse of time. Within certain magnetic storage systems, data can be preserved with remarkable stability over extended periods. This capacity arises from the intrinsic properties of the magnetic materials involved. The alignment of tiny magnetic domains in these systems can remain undisturbed for many years. Each domain, a small region within the magnetic material, holds a specific orientation, encoding bits of information in a precise manner. Over time, even without power or constant use, these aligned domains do not easily lose their orientation. As a result, the stored data remains intact, safeguarded against gradual changes that might affect other types of media. This stability offers a quiet assurance that the encoded information can be retrieved long after it was originally written. Each magnetic layer within the storage medium plays a role in this durability. The materials themselves are engineered to resist environmental influences, ensuring the longevity of the data. As time passes, these magnetic structures quietly maintain their integrity, waiting patiently to reveal their hidden contents whenever needed. This serene interplay of magnetism and time creates a gentle reassurance, allowing the cycle of information to continue peacefully, quietly resting until called upon once more. Magnetism has a subtle yet fascinating ability to create energy that lies quietly in the surroundings. This hidden energy exists as magnetic potential energy, nestled within the magnetic fields generated by both magnets and electric currents. Each magnet possesses a field that extends beyond its surface, an invisible blanket wrapping around it. This field is not merely empty space, it is filled with potential energy waiting to be recognized. When a magnet is near another magnet or an electric current, the interaction of their fields can create forces that may either attract or repel. This relationship allows for a dynamic interplay, with energy stored in the form of these magnetic fields. As they fluctuate, shifting in response to movements or changes in current, the magnetic potential energy remains present, silently poised for transformation. The arrangement of charged particles within the magnet determines the strength and orientation of the field, giving rise to the potential energy that exists in this system. Each field patiently holds energy, ready to be released when circumstances allow, embodying a gentle balance between force and rest. This quiet energy resides in the spaces around us, weaving an unnoticeable fabric of magnetic influence, inviting deeper exploration whenever the time is right. Sedimentary rocks hold within them stories of the earth, whispering secrets from long ago. During their formation, these rocks can capture magnetic minerals, anchoring them in layers over time. Each grain of these minerals acts like a tiny compass, aligning itself with the magnetic field of the planet as it settles into place. This alignment creates a record, preserving the orientation of the Earth's magnetic field at the very moment the rock was formed. As these layers build, they become a chronicle of changes, reflecting shifts in the planet's magnetism over millions of years. The magnetic minerals, quietly entombed within the rock, retain the memory of those ancient fields, revealing how the Earth has transformed. Observing these patterns allows scientists to glimpse the dynamic nature of our planet, uncovering the ebb and flow of its magnetic history. These records remain undisturbed for vast stretches of time, waiting patiently for discovery. The gentle layers of sediment hold this information tightly, inviting exploration and understanding of the Earth's magnetic past, a soft testament to the ever-changing forces that shape our world. Within the layers of sedimentary rocks, the magnetic signatures of ancient environments lie quietly preserved. As these rocks form, minerals settle and align according to the Earth's magnetic field at that moment. Each layer becomes an archive of the past, capturing the essence of the climate and geological conditions that existed long ago. Over millions of years, these records accumulate, allowing the rocks to hold memories of shifting climates, tectonic activity, and even changes in sea level. As the world transforms, so too do the environments in which these sediments accumulate. Deep ocean floors, riverbeds, and ancient lakes all leave behind distinct signatures woven within the rock, each layer quietly telling its story. When studied, these magnetic signatures unveil insights into the Earth's history, revealing patterns of warmth and cold, wet and dry. The gentle layers, rich with these magnetic tales, stand as a testament to the planet's dynamic nature. They invite curiosity, holding within them the whispers of countless eons, waiting for the moment when they might share their silent histories with those who seek to understand. The Earth's magnetic field is not static. It is a living, dynamic system that shifts in subtle yet significant ways. Over time, this field undergoes gradual changes, allowing magnetic poles to move their positions by several kilometers each year. This slow drift is part of a natural cycle, influenced by the movement of molten iron within the Earth's outer core. As these currents flow, they create fluctuations in the magnetic field, which can alter its strength and orientation. Poles that once stood firm may gently wander, tracing new paths across the surface of the planet. These movements can be quiet and soft, a slow dance of the Earth's core, shaping the magnetic landscape above. The layers of sedimentary rocks, with their stories embedded in magnetic signatures, illustrate these shifts, recording the changing influence of the magnetic field over countless years. As the poles shift, they invite us to ponder the intricate nature of our planet, a tapestry woven from the silent rhythms of time. Each gentle alteration in the magnetic field weaves another thread into Earth's ongoing story, waiting patiently to be discovered. Magnetic fields in the universe exhibit an astonishing range of strengths, with some phenomena reaching incredible densities. Among these, magnetars stand out, harboring magnetic fields that can soar to about 10 circumflex, 11 teslas. These dense fields are forged in the hearts of dying stars, where devastation transforms energy and matter in ways that are difficult to fathom. In these cosmic giants, the immense gravitational forces and the collapse of the star's core create conditions ripe for such extreme magnetism. The energy density achieved is a marvel of astrophysical processes, impacting the nearby space with tremendous force. Waves of energy radiate from these magnetars, influencing surrounding particles and transforming the very fabric of the environment. As these magnetic fields pulse and shift, they engage with the universe in quiet conversations, weaving a complex tale of energy and matter. Each pulse carries with it the essence of the star's life, highlighting the intricate balance of forces at play. The fascination with these celestial wonders invites a sense of peace as their distant energies remind us of the boundless mysteries lingering in the cosmos, patiently unfolding in their own time. Permanent magnets, particularly those crafted from rare Earth elements, possess a noteworthy property known as coercivity. This characteristic allows them to maintain their magnetism with impressive stability over extended periods. In a quiet room or a hidden corner, these magnets stand resolute, shielding their magnetic field with steadfast presence. The extraordinary strength of these magnets comes from their internal structure, where the arrangement of atoms plays a crucial role. The alignment of magnetic moments within the material creates a field that endures against the gentle pull of demagnetizing influences. However, when subjected to extreme conditions such as intense heat or strong opposing magnetic fields, even these resilient magnets can begin to degrade, gradually losing their magnetic properties. Over time, the degradation can be subtle, unfolding in slow shifts rather than immediate changes. Each particle remains a silent witness to the surroundings, navigating through seasons of temperature fluctuations and varying pressures. Such transformations weave into the long narrative of these magnets, illustrating the delicate balance of stability and change. Each moment holds stillness while the world shifts around, inviting a sense of calm that lingers softly in the air. Magnetic susceptibility reflects how a material interacts with an external magnetic field, offering insights into its internal character. When a magnetic field is introduced, the atoms within the material respond with subtle shifts. They align to varying degrees with the field, revealing their inherent magnetic nature. This response is stable and consistent over time, remaining undisturbed unless the material experiences significant structural changes or encounters radiation. The delicate dance of atoms maintains a quiet harmony. Each particle, in its own space, contributes to the overall behavior of the material, ensuring that its magnetic susceptibility reflects a balance of forces. In absence of external disruptions, this property can endure for long periods, encapsulating a moment of stability. When exposed to extreme conditions, such as high-energy radiation or dramatic alterations in structure, the responses of the atoms can change noticeably. This transformative process unfolds gently, sometimes unnoticed, yet it adds layers to the material's story. Here, within the stillness, lies the essence of magnetic phenomena, resonating softly with every subtle shift in energy and position, reminding us of the quiet complexity that exists in all matter. Certain magnets are composed of alloys, which are harmonious blends of different metals brought together in a seamless union. These mixtures create a unique internal structure, integrating the properties of each metal. The careful combination can enhance the overall stability and strength of the magnet's magnetic properties, leading to a resilient form that endures over time. Within these alloys, the interactions between the different elements work together, fine-tuning the magnetic response. As each metal contributes its characteristics, the result is a material that can maintain its magnetism for extended periods. The balance established within the alloy means that it can resist changes that typically affect individual metals, allowing for a longevity that is quite remarkable. Even in the gentle ebb and flow of environmental conditions, these alloys remain steadfast. Their ability to retain magnetic strength serves as a quiet testament to the molecular dance occurring within. In this calm, unhurried world of magnetic materials, the lasting nature of these alloys continues to unfold with each moment, exploring the delicate relationships between the particles that shape their existence. Breathing softly, a sense of stillness embraces the room. Each moment unfolds gently like leaves, swaying in a quiet breeze. The mind finds solace in the knowledge that the world of science continues in its own serene rhythm, even as the day draws to a close. Magnetism, like a whispered promise, remains steady and unwavering, nestled in the heart of each alloy. The quiet dynamics of nature weave together, creating a tapestry of calmness that envelops us. Thoughts drift lazily, as if carried by the soft, undulating currents of a gentle stream. Each particle, each moment, exists in a state of tranquility, resting in the simplicity of its nature. There is comfort in allowing everything to slow down. Mind and body begin to feel lighter, as if floating on a cloud of soft, soothing air. In this peaceful space, a sense of completion settles softly, like a warm blanket on a cool night. The day's curiosities have been explored, lingering gently in the mind, ready to be embraced once more in dreams. As the last whispers of consciousness float away, a gentle invitation to rest emerges. Letting go of the thoughts, welcoming the stillness, the world grows dimmer, softer, and welcoming. Good night from Sleepy Science Facts.